And can you use references from experiential time to make statements about physical time? So these are some of the fundamental questions that I think of when I deal with this, what Professor Barbour calls a very slippery topic. So David Albert will begin.
Thank you for inviting me here. This is going to be a much more modest talk than the one we heard, say, from Professor Ellis yesterday afternoon. But I guess it's still going to engage it in some way. In particular, it's going to try, in its small way, to gesture in the opposite direction of that talk. Professor Ellis's talk was aimed, at least in part, at setting up boundaries of the scientific project. And this talk is going to be aimed, at least in one particular case, at removing them. So the business of saying something interesting about the passage of time, the business, for example, of getting to the bottom of our impression that it's the past that gives rise to the future and not the other way around, the business of getting to the bottom of our impression that the future is open and the past is settled, the business of getting to the bottom of our impression that by acting now we can affect the future but not the past, all of that stuff has almost always been taken to be a matter for some sort of conceptual or linguistic or metaphysical or phenomenological or theological analysis, and not a proper subject of study for the natural sciences at all. The business of the natural sciences, according to this view, is to discover fundamental laws and mechanical processes whereby the past discover the fundamental laws and mechanical processes whereby the past shapes or produces or gives rise to the future. But as to the fact that it is the past that gives rise to the future rather than the other way around, that has always been taken to be something prior to and deeper than and outside of the jurisdiction of scientific explanation, something that amounts, as a matter of fact, to a condition of the possibility of scientific explanation. And one way of understanding the project I want to tell you a little about today is as an attempt at resisting all of that, an attempt at enlarging the proper subject of study of the natural sciences, an attempt more particularly at understanding these features of what we're used to calling the passage of time as a mechanical phenomenon of nature. Let me start off, because this is what it's going to be based in, by reminding you of the basic logical structure of classical statistical mechanics. Statistical mechanics begins with a postulate to the effect that a certain very natural-looking measure on the set of possible exact microconditions of any classical mechanical system is to be treated or is to be understood as a probability distribution over those microconditions. The measure in question here is, as a matter of fact, the simplest imaginable measure on the set of all possible exact microconditions of whatever system it is one happens to be dealing with, the so-called Lebesgue measure on the phase space of the possible exact positions and momenta of the Newtonian particles that make the system up. And the thrust of all of the beautiful and ingenious arguments of Boltzmann and Gibbs and of their various followers and collaborators was to make it plausible that for any true thermodynamical law to the effect that macro condition A evolves over such and such an interval under such and such external circumstances into macro condition B, then the overwhelming majority of the volume of the region of phase space associated with macro condition A on the above standard measure in phase space is taken up by micro conditions which are sitting on deterministic Newtonian trajectories which pass under the allotted circumstances at the end of the allotted interval through the region of phase space associated with the macro condition B. That's the structure of the explanation of macroscopic regularities to the effect that A typically evolves into B. And if these arguments succeed, and if Newtonian mechanics is true, then the above-mentioned probability distribution over all microconditions is going to underwrite great swaths of our empirical experience of the world. But there's a famous trouble with all this, which is that all of the above-mentioned arguments work just as well in reverse. That all of the above-mentioned arguments entail not only that a half-melted block of ice sitting at present in a warm room will be more melted 10 minutes from now than it is at present, but also that it was more melted 10 minutes ago than it is now. And it's reasonable to say, I think, that we're as sure as we are of anything that the latter claim isn't right. And the canonical method of patching this trouble up is to supplement the dynamical equations of motion and the statistical postulate with a new and explicitly non-time reversal symmetric fundamental law of nature, a so-called past hypothesis, to the effect that the universe had some particular simple, compact, symmetric, cosmologically sensible, very low entropy initial macro condition. The patched up picture, then, consists of the complete deterministic microdynamical laws and a postulate to the effect that the distribution of probabilities over all of the possible exact initial microconditions of the world is uniform with respect to the Lebesgue measure over those possible microconditions of the universe which are compatible with the initial macro condition specified in this past hypothesis, and zero probability of it being elsewhere. And with that amended picture in place, the arguments of Boltzmann and Gibbs make it plausible not only that the paper will be yellower and the ice cubes more melted and the people more aged and the smoke more dispersed in the future, but that they were all less so, just as our experience tells us, in the past. With that additional stipulation in place, to put it another way, the arguments of Boltzmann and Gibbs make it plausible that the second law of thermodynamics remains in force all the way from the end of the world back to its beginning. What we have from Boltzmann and Gibbs, then, is a probability distribution over possible initial microconditions of the world, which, when combined with the exact deterministic microscopic equations of motion, apparently makes good empirical predictions about the values of the thermodynamic parameters of macroscopic systems. And there's a question about what to make of this success. We might take this success merely as evidence of the utility of that probability distribution as an instrument for the particular purpose of predicting the values of those particular parameters, or we might, more ambitiously, take that success as evidence that the probability distribution in question is literally true. And note, and this is something worth pausing over, that if the probability distribution in question were literally true, and if the exact deterministic microscopic equations of motion were literally true, then this probability distribution, combined with those equations of motion, would necessarily amount not merely to an account of the behaviors of the thermodynamic parameters of macroscopic systems, but to the complete scientific theory of the universe. Because the two of them together assign a unique and determinate probability value to every formulable proposition about the exact microscopic physical condition of whatever physical things there happen to be. If the probability distribution and the equations of motion in question here are regarded not merely as instruments or inference tickets, but as claims about the world, then there turns out not to be any physical question whatsoever on which these principles turn out to be jointly agnostic. If the probability distribution and the equations of motion in question here are regarded not merely as instruments or inference tickets, but as claims about the world, then either they are false, or they are, in some sense, of which more in a minute, all the science there can ever be. And precisely the same thing is manifestly going to apply to any probability distribution over the possible exact initial conditions of the world, combined with any complete set of laws of the time evolutions of those conditions. And some of us who work in the foundations of statistical mechanics, this was actually Barry Lower's idea, I think, have lately taken to calling this probability distribution over trajectories the mentaculus, after the notebook of a psychotic character in a wonderful Coen Brothers movie called A Serious Man from about 2 years ago. Anyway, I want to look into the possibility that this probability distribution that we have from Boltzmann and Gibbs, or something like it, something more up to date, something adjusted to the ontology of quantum field theory, or quantum string theory, or quantum brain theory, is true. And this distribution turns out to have a simple and conspicuous, and profoundly illuminating things to tell us, not only about the second law of thermodynamics and about the preponderance of outgoing over incoming radiation and so on and so forth, but also about the temporal asymmetry of epistemic access, the fact that the kinds of things we know about the past and the ways we have of knowing about the past are profoundly different from the kinds of things we know about the future and the ways we have of knowing about the future, and also about the asymmetry of intervention, about our impression, that is, that by acting now we can affect the future and not the past that I was talking about before. Okay. What it amounts to explain this or that as a mechanical phenomenon of nature, is to show how it can be extracted, at least in principle, by means of the appropriate sorts of conditionalization from this master probability distribution I've called the mentaculus. That's what's going on, and that's all that's going on according to this way of thinking. When we explain why a certain projectile lands on this or that particular patch of the surface of the Earth, or how an atomic clock works, or why ice melts in warm rooms, and so on. And these explanations require no metaphysical or conceptual or linguistic or phenomenological distinctions whatsoever between past and future, or even for that matter between time and space. And this is something we can go into, I'd be happy to go into more in the discussion period, because it may impact very directly on the topic of this conference. And insofar as I can tell, there isn't any principled obstacle standing in the way of precisely this sort of an explanation. That is, an explanation that appeals to no metaphysical or conceptual or linguistic or phenomenological or theological distinctions whatsoever between past and future, or even between time and space. Insofar as I can tell, there isn't any principled obstacle standing in the way of precisely this sort of an explanation of the asymmetry of our epistemic access to the past and future, and, more interestingly, of the apparent susceptibility of the future, but not the past, to influences from the present. The business of actually putting these explanations together is a large undertaking, and it's the work of a growing number of different investigators, and it's still very much underway and very much incomplete. And I'm not going to be able to give you anything along the lines of an exhaustive or systematic description of that project in the time I'm allotted here, but I want to point to one or two fundamental observations that I hope will suggest something of how such explanations might ultimately look. Consider, to begin with, two different procedures for making intertemporal inferences. One, Start with some collection of facts, F, about the physical condition of the world at time t. Put a probability distribution which is uniform with respect to the standard measure on phase space over all of the possible microconditions of the world which are compatible with F. Evolve that distribution forwards or backwards in time by means of the microscopic equations of motion so as to obtain information about the physical condition of the world at other times. Let's make up a name for a procedure like this. Call this inference by prediction if the other time in question is in the future of t, and call it inference by retrodiction if the other time in question is in the past of t. The entirety of what we justifiably believe about the future, I suspect, can in principle be obtained by prediction from the entirety of what we justifiably believe about the present. But retrodicting from what we believe about the present is a notoriously terrible way of drawing conclusions about the past. One of the lessons of the work of Boltzmann and Gibbs, for example, is that retrodicting from what we know of the present is going to imply that the half-melted ice cube in the glass of water in front of me was more melted 10 minutes ago than it is now, that I have never looked younger than I do now, that Napoleon never existed, and so on. Good. Second method of inferring between different times. Start with two collections of facts about the physical condition of the world, F1 and F2, where all the facts in F1 pertain to some particular time, T1, and all the facts in F2 pertain to some other particular time, T2. Put a probability distribution which is uniform with respect to the standard measure on the phase space over all of the possible microscopic histories of the world, which are compatible with both F1 and F2 and the microscopic equations of motion, and use that distribution to obtain information about the physical condition of the world at times between T1 and T2. Okay? So prediction and retrodiction involves starting in one place and inferring using the laws information about another place. What I'm calling inference by measurement involves starting with information about two times and making inferences from them to conditions at a time in between. Good. Call this inference by measurement. Inference by measurement is so called because it's modeled on the logic of measuring instruments. Measuring instruments, that is, are the sorts of systems which reliably undergo some particular transition when they interact in the appropriate way with the system they're designed to measure. They undergo this transition, that is, only in the event that the measured system is at the time of the interaction in one or another of some particular collection of physical situations. The record that emerges from a measuring process is a relation between the conditions of the measuring device at the two opposite temporal ends of the interaction. The record-bearing conditions of the measuring devices which obtain at one temporal end of such an interaction are reliable indicators of the situation of the measured system at the time of the interaction, only in the event that the measuring device is in its ready condition, the condition, that is, in which the device is calibrated and plugged in and facing in the right direction, and in every other respect all set to do its job at the interaction's other temporal end. The sort of inference one makes from a recording is not from one time to a second time in its future or past, as in the case of prediction and retrodiction, but rather from two times to a third that lies in between them. And note that inferences by measurement can be immensely more powerful, that inferences by measurement can be immensely more informative than inferences of the predictive retrodictive variety. Think, for an example, of an isolated collection of billiard balls moving around on a frictionless table. And consider the question of whether or not, over the next 10 seconds, billiard ball number 5 is going to collide with any of the other billiard balls. The business of answering that question by means of prediction is plainly going to require a great deal of calculation, and that calculation is going to require as input a great deal of information about the present, It will require, in particular, a complete catalog of the present positions and velocities of every single one of the billiard balls on the table. But note that if we happen to know, by hook or by crook, that billiard ball number 5 was moving 10 seconds ago, then the question of whether or not billiard ball number 5 happens to have collided with any of the other balls on the table over the past 10 seconds can be definitively settled in the affirmative without any calculation at all, merely by the single binary bit of information that billiard ball number 5 is currently at rest. And note that whereas the information that billiard ball number 5 was moving 10 seconds ago and that it is now at rest is going to suffice, completely irrespective of how many billiard balls there are on the table, to settle the question of whether or not billiard ball number 5 was involved in a collision over the past 10 minutes. The amount of information we're going to require in order to determine, by means of prediction, whether or not billiard ball number 5 will be in a collision over the next 10 minutes is going to rise and rise without limit as the number of billiard balls on the table rises. But there's an obvious puzzle about how it is that inferences by measurement can ever actually manage to get off the ground. The game here, after all, is to look into the business of making inferences from one time to another. The game, more particularly, is to look into what we can know about the complete history of the world from the vantage point, as it were, of the present. And in the context of an investigation like that, the facts that it's going to be appropriate to think of as unproblematically given to us, the facts from which it's going to be appropriate to think of these inferences as starting out, are presumably going to be limited to facts about how the world is now. Consider, for example, the case of the billiard balls. If I happen to know that billiard ball number 5 was moving 10 seconds ago, then I need know no more of the present state of the entire collection of billiard balls than that billiard ball number 5 is currently at rest in order to conclude that billiard ball number 5 has been involved in a collision over the past 10 minutes. But how is it that I ever do happen to know that billiard ball number 5 was moving 10 minutes ago? Well, presumably by measurement. Presumably, that is, because I have a record of it. But how is it that I know that the purported record in question is actually reliable? How is it, that is, that I know that the measuring device which presently bears the purported record of billiard ball number 5's having been in motion 10 seconds ago was in fact in its ready condition at the appropriate time prior to 10 minutes ago? Presumably by means of another measurement. And before you know it, a ruinous, world-devouring regression is underway, which can only be stopped by means of something which we can be in a position to assume about some other time, something of which we have no record, something which cannot be inferred from the present by means of prediction, retrodiction, something to which a sufficiently relentless investigation of the ultimate grounds of our knowledge of almost anything we know about the past, that the half-melted ice in front of me was less melted 10 minutes ago than it is now, that I once looked younger, that Napoleon existed, and so on, something that a sufficiently relentless investigation of the ultimate grounds of anything like that must eventually lead back to the mother, as it were, of all ready conditions. And the thought is that there's an obvious candidate for just such a mother sitting right at the center of the standard statistical mechanical account of the second law of thermodynamics in the past hypothesis. The thought is that it's because the fundamental physical laws contain a past hypothesis, but no analogous future one, that facts about the present can be so mind-bogglingly more informative about what's already happened than they ever are about what's to come. The thought is that there can be measurements of the past but not the future because there's something in the past but nothing in the future to put an end to the regress. And it turns out that the flip side of all this has a lesson in it about the asymmetry of intervention. Think again about the collection of billiard balls. And suppose, and this is what's going to stand in the context of this very simple example for a past hypothesis, suppose that billiard ball number 5 was moving 10 seconds ago. What we learned about that sort of a collection of balls in the discussion of the asymmetry of epistemic access was that whether or not ball number 5 will be involved in a collision over the next 10 seconds depends on more or less everything about the present condition of every single one of the balls on the table. Whether or not whether or not ball number 5 has been involved in a collision over the past 10 seconds can, at least in some cases, be settled by the present condition of ball number 5 all by itself. And so, very crudely, almost anything about the physical condition of the world at present can affect whether or not ball number 5 will be involved in a collision over the next 10 seconds. But almost nothing about the physical condition of the world at present, nothing in this particular case, save the present state of motion of ball number 5 itself, can affect whether or not ball number 5 was involved in a collision over the past 10 seconds. And so there are, as it were, a far wider variety of potentially available routes to influence over the future of the ball in question here. There are a far wider variety of what you might call causal handles on the future of the ball in question here than there are on its past. And all of this is going to generalize quite straightforwardly, if all goes well, to cases of worlds which are much richer and much more complicated and much more like our own. And this is how one can begin to link these three asymmetries: the thermodynamic asymmetry of ordinary physical processes, the asymmetry of epistemic access, and the asymmetry of intervention together. But all this as it stands is at best only a suggestive beginning, and it raises at least as many questions as it answers. What's worried almost everybody about this approach in particular is that it seems to imply that the distinction between our control over the future and the past is a matter of degree, whereas that distinction presents itself to us in our everyday experience of the world as something absolutely and infinitely sharp. And this has been much discussed over the 10 years or so since these suggestions were first written down, and much has been learned about it over that period. But that's another story, and a rather long story, and I think it'll have to be saved for some other time. Thank you. So we're going to do the questions later, is that right?
Yes, that's right.
Good.
Now my pleasure to introduce Julian Barbour, who has really shaken things up in the time controversy.
We need the electronics now. Well, while that's getting ready, let me give my warm thanks to the organizers and disclaim any credit for the title of my talk, which is The Slippery Question, What is the Nature of Time? That was suggested to me by James. He asked the speakers to address that question. Right, I think we're ready to go. Here's a quick overview of what I want to talk about. I'm going to try to be radical. I want to try and say, first of all, what I think an instant of time is. I want to say something about how simultaneity is defined. And then, very important is what I call the forgotten question: what is duration? It's the Cinderella of the questions about time. Then I'm going to go into the evidence that the quantum universe may be static and change an illusion. And that will, when I'm discussing that, that will perhaps suggest that if we get rid of time, we can move from the situation where science is only able to say how, and possibly move it in the direction of where it can say why. Now, I'm tentative about that, but I think there is some indication that that's quite interesting, really. And following on immediately from David's talk, I think it may also suggest why we don't actually need the past hypothesis, that we may be able to find a deeper explanation of it than having to postulate it. I agree entirely that you can do a great deal with it once it's postulated, but I think there is a possibility that it's not necessary and that it can be explained from deeper things. I'm going to ask why it is that we see motion. Why does time seem to have a direction? And finally, perhaps that's related to what I've already said, why do things come to be? Now, I've just said I don't believe in time, but there's a very obliging thing here with, so I don't need to take my watch off, telling me what the time is. I want to start by just, I'm not going to be at all technical. I'm going to just do a bit technical for those who understand it when we get to the theory of duration. I will inevitably have to bring in scientific concepts. Now, I first of all want to say that there are two totally distinct notions of relativity which unfortunately get greatly confused. There is the famous Einsteinian relativity, where he divides space and time up in different ways, as illustrated. There's how one observer in relativity, in special relativity, but to some extent also in general relativity, will divide up space and time. That's time going upwards and space horizontally. And this is how another observer will do it. And they are at angles to each other, and space and time get mixed up. And that was perhaps the single most remarkable suggestion of physics in the 20th century. Now, Einstein was stimulated to work on relativity by earlier remarks, 20, 30 years earlier, by Ernst Mach, where he said that position and motion is relative. And he meant something quite different, that the position of an object, this object here, is defined relative to all the other objects at a given time in the universe. And that's a completely different notion of relativity. And I'm inclined to think that the Machian one is the more fundamental one. And if you apply these ideas of Mach consistently, I think it does cast some doubt, at least, on Einsteinian relativity. And I'm going to invoke no less a person than the great Paul Dirac, one of the great creators of quantum mechanics, who did some work on trying to reconcile Einstein's general theory of relativity with quantum mechanics, and came out, as a result of what he discovered, with this very remarkable sentence: I'm inclined to believe that four-dimensional symmetry is not a fundamental property of the physical world. He said that in about 1958. I read that one sentence in 1963. It completely and utterly changed my life, and I've been trying to make sense of that one single sentence ever since. And I think with collaborators have made, luckily, a little bit of progress. Now, let me just say about simultaneity in general relativity. This is the problem that you have. It's called foliation invariance, or the lack of simultaneity in general relativity. Sorry, I should have gone back again. I want the pointer. This is a picture of space-time. There's time going up like that, and here's space in this way. And you can define quite different nows. This is one way of defining an instant of time over the whole universe, but that's completely arbitrary. By the way, each of these instants are like that picture that I showed you before of Machian relativity, but there's no way to say that one is distinguished above another. There's no unique sequence of them in Einstein's theory. And that leads to the problem that if you try to say you can't pick out a unique history in Einstein's theory as he originally formulated it. The blue ones here, this is history. This would be one state of the universe at an instant of time as you've tried to construct it. But there's an alternative one. As Bryce DeWitt put it, there is not a unique geodesic, there's not a unique history of the universe. There's a sheaf of histories. And there's merely the block universe. Now, Dirac found this very difficult, and he actually, quite brutally and in an ad hoc way, when he was trying to create a quantum theory of gravity, imposed a unique history. Now, I think actually the Machian arguments do enable one to make that more plausibly and not in the ad hoc way that Dirac did it. And let me say that what comes out, and it's essentially what Dirac did introduce ad hoc, there is one particular way of dividing up space and time, creating a foliation in it, which I think nearly all relativists and I speak in the presence of George Ellis, who's a very distinguished relativist and a great expert in these things too, and Martin Rees here, would agree that if there is a distinguished way of dividing up Einstein's miraculous space-time, it is in what is called, by means of foliations of constant mean curvature. Now, you're all familiar with soap bubbles. These are the most beautiful things when you blow a soap bubble, and it has a perfectly uniform curvature, a surface like that. And that is clearly something which is geometrically distinguished. Now, that's a surface of 2 dimensions in 3-dimensional Euclidean space. Now, there are analogous things sitting within inside Einstein's 4-dimensional space-time, exactly analogous to soap bubbles, and they played a hugely important role in work done 40 years ago by somebody called James York, which has become actually the basis of numerical relativity. It's an incredibly important part. And when you take Machian ideas seriously, and I'll say a little bit about how seriously you have to take it, these surfaces arise in a very natural way. So I think this is perhaps suggesting that there is, after all, a notion of absolute simultaneity sitting within inside general relativity. And John Wheeler conjectured this 40 years ago. But I won't say much about that. Now I want to come into, because that's going to be too technical to do that. Now I want to talk about what I think is an instant of time. Now normally people, when they talk about an instant of time, they sort of pick it up a bit from Newton, what Newton said, and I'll quote him in a moment. But they think of it really as a mathematical point on a line. This is one instant of time. That's how it's represented. T is your independent variable in dynamics, and it has a certain set of values as you go along the line. And it's completely featureless, has nothing to distinguish it. Now, I think this is complete and utter rubbish. How do I know what the instant of time is? What it looks like to me when I look out and see you, in the immediate purpose. And if you go back to more primitive societies, that's how they thought about the now. It's how things are arranged in the world. And in fact, if you look up the Greek word onta, it says existing things, second meaning, the present, as opposed to the past and the future. So I think that the way that one should think about an instant of time is that it's a configuration of the universe. It's the way that the universe is arranged, its shape. Now, this only makes real sense, and I was hinting at this yesterday, and agreeing, I think, with George in some sense about not liking an infinite universe. This only really makes clean sense if in some senses the universe is a closed system in the context of Einstein's theory of gravitation, if it's what we call spatially closed. That's like the surface of the Earth. The surface of the Earth, if you go far enough, you come back to where you were. And it's only then, as Einstein said, and I think very correctly, it's only then that you can get a complete and satisfying account. You can close the circle of cause and effect. Now, the other thing about this is I'm representing it here by one particular example of just particles, like Newtonian point particles, but much more general notions of configuration are possible, configurations of fields, structures of fields. And these do not exist in space. You mustn't think that they're sitting somewhere in space. They're just defined relative to each other. So in this picture, the universe is like bees swarming in nothing. And a significant question is, how are we going to describe a history of the universe in classical terms when that's the case? And that's where I will talk a little bit of, and give you a little bit of technical detail. Now, let me go on to the next one. I'm going to show you a few of these pictures of instants of time, just sort of by repetition 3 times. You shouldn't repeat more than 3 times. Shakespeare wouldn't do it. Tomorrow and tomorrow and tomorrow. But I have a nasty feeling I might have 4 of these pictures, but it'll be a while before you get to it again. Simul comes from the Latin at the same time. Configurare means to fashion together. I think this is something, and I'll say more about this in a moment. I think configurations express the integrity of the universe. or perhaps it would be better to say, because I'm going to have to say what I mean by the universe, the integrity of an instant of time. It's somehow fashioned together, and I will say something about that in just a moment. Let's see what Newton said on time and space. That's the third one. Too many. Absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external, and by another name is called duration. And Newton insisted that even if nothing changed, time would be passing. He's quite emphatic about that. Absolute space in its own nature, without relation to anything external, remains always similar and immovable. And I'm sure you know that there was a great debate between Leibniz and Newton about the nature of space and time. And I'm getting into trouble with Shakespeare. Leibniz said nothing of the sort as what Newton says. He says space is the order of coexisting things, and time is the succession of coexisting things. Should note that both Newton and Leibniz assume space is Euclidean. Now, there was the question raised by Michael yesterday, what is a thing? And one of the most wonderful things, I think, in Leibniz's writings is he talks about pluralities within a unity, a plurality within a unity. And he's clearly groping to say, what is a true unity? He says a true unity is not like a heap of stones by mere aggregation, where you throw something on top of it. There must be something more to it. There must be some true principle which knits it together in an indissoluble way. And I think he's groping for it. To anticipate, I would say, I think he was groping for group theory. And I will say something about that now. If you have, let's just say remember how the ancient Egyptians, 4,000 years ago, discovered Pythagoras' theorem. They measured distances between points on the surface of Egypt. And they measured, if you measure the distances between n points in Euclidean, three-dimensional Euclidean space, you get n into n minus 1 divided by 2 positive numbers. Now, so if you have 10, you get, so for 10, n equals 10, you get 45 distances. And these are empirical facts. These are numbers found by measurement. It's very easy to pick up measuring rods and measure the surface of the Earth in Egypt. Those positive numbers could be completely arbitrary. But the really great discovery, the first really great discovery in science, was that they are not completely arbitrary. Really good mathematicians, given those 45 positive numbers, looking at them long enough, could suddenly say, these satisfy very special algebraic relationships. Certain combinations of them put together equal 0. And that's something very, very remarkable. And that is actually, I think, the principle of unity that Leibniz was seeking for. Once you do that, it's amazing how much of very deep and important mathematics comes straight out of it. You have the possibility then of representing those 45 distances. The same content can be represented by 30 Cartesian coordinates. This is data compression. When you come to something like a globular cluster with 1 million stars in it, you have 10 to the 12, 1 million times 1 million, essentially, distances between the stars, but you can represent them by 3 million coordinates. That is data compression on a colossal scale, and it is all characterized by the Euclidean group, by the facts of Euclidean geometry. Very, very striking. And I think this is actually what Leibniz was groping for, some of that, at least partially. It's at least an illustration of his idea of a plurality within a unity. This is the plurality, all those distances, and the unity is that magical relationship which comes out. And let me mention in this connection Goethe's Faust, where Faust is desperately seeking for the secrets of the world. And he asks, Was im Innersten die Welt zusammenhält. What is it that in its innermost core holds the world together? And for science, I think it's geometry. And Galileo said, he that attempts natural philosophy without geometry is lost. And it's geometry, I think, and not time that is going to be spatial geometry, which I think is so important. Now, what is the universe? People throw the universe around. Now, there was quite a precise definition of various multiverses from Priya yesterday. When I talk about the universe, I mean what is called the configuration space of the universe. It's all possible configurations that the universe can have, so it's all possible instants of time that constitute the universe. So instants of time constitute the universe. Now this is, I believe, a vastly richer notion of time than anything to do with linear time as is normally presented. And the other thing is, there is a unity, again to come back to this need for a unity in describing things. Each configuration that the universe could have is different from every other, but they're all constructed according to the same rules. If the universe is described by 10 points in Euclidean space, then they all have to satisfy those same relations. There's a unifying rule that creates the entire space of possibilities. George Ellis was mentioning spaces of possibility very often in his thing. This seems to me extremely important. Leibniz is all about spaces of possibility. And the space of possibility is created once you've got one configuration, once you've found one configuration with 10 particular points on the surface of Egypt, you've got the notion of all different points on the surface of Egypt, all knit together by the same rule, but different instantiations of that same rule. Now, I'm just going to go very quickly on to the next bit to give you just a little bit of equations. How do we... I said that the universe, the classical universe, is like bees swarming in nothing. And how are you going to say where anything has moved? Why? This is why Newton introduced absolute space, because he wanted to be able to say that an object, if it's left to itself, will move in a straight line at a uniform speed. He was forced to introduce the notion of absolute space to do that. Now, there is an alternative Machian way of doing it, and this is the following way. Let's just suppose we had 3 particles in a universe, nothing else, just 3 particles in good old Euclidean space. And in one instant, they form a triangle, this blue triangle here. And it has a particular shape and size. I'll allow a size at this stage of the discussion. And then in a different instantiation, in a different instant, that triangle is different. They've changed, they've moved relative to each other. But there's no way in which you can objectively say how they've moved in space. So how can you measure what the change is, what the difference is? That's the key question. Well, there's quite a nice, there is actually one way, because if I just come along and put down, oops, sorry, I should have gone back that one, still not got the laser pointer right. If I could put the triangle down in any completely arbitrary way I like, and in each position, I find that particle 1 has gone from here to here, but it's a different one depending on where I put the second triangle relative to the first. And it was to solve that problem that Newton introduced absolute space. Now, Mach comes up essentially with an alternative one. He says it's somehow relative. You must do it by relationships one to the other. And so what you do is you maneuver the second triangle, the red one, around relative to the blue until you try and bring it to the best matched position, where they're sitting as close as they can on top of each other. Now, geometry is based on congruence. You say that 2 figures are congruent if you can imagine moving them around in space until you get them to exact coincidence. Now, if things are changing, you can't do that. But what you can try and do, the figures, the triangles are incongruent. What you can try and do is minimize the incongruence by bringing them into this position where there's a certain quantity, which I've written down here. Essentially, what you get wherever you put the triangles, you will always get little distances dx here where particle 1 has moved, particle 2 and particle 3 have moved. So you take these little distances and you take their product, you multiply them by themselves, their norm, so you take their square, you weight them with the masses here, and you add up those quantities there. Now this is something I won't go into. This is just to actually to introduce interactions between the particles, but that's not essential to my point. And then you have to take a square root because you want a distance, which is a square root of something which is quadratic. This is Pythagoras' law. So you take a square root, and that square root is actually getting rid of time. It's actually very easy to eliminate time entirely from physics. You just take a square root of a quantity like that. That's all you need to do. So that then tells you how much the one triangle has changed relative to the other. And that is actually, you can call that a distance between those triangles. That is a difference between the triangles. It's a distance between them. And now you can imagine moving through the space of all possible triangles, and you want to go to from A to B, where you minimize this quantity down here, which is telling you how different they are. So each step, you see how much difference you've created. You go from A to B in the configuration space of the universe and find out which is the shortest path. And then you say, that is the history that I've gone through. And rather wonder, I'll jump onto that because otherwise I'll be going out of time. Now, rather wonderfully, it turns out that this gives you Newtonian dynamics, but with a very strong restriction. Well, I will go back again. This is the particle at a given, the three particles at a given instant, the triangle that they form. That's their center of mass. Now, these represent the velocities they have when I've put the second triangle on top of the first in the best matched position. And those velocities, or momenta here, are very strongly restricted by that best matching condition. In Newtonian theory, they can go anywhere you like. This is the difference between Machian dynamics and Newtonian dynamics. In Newtonian dynamics, those red arrows can point anywhere you like, so that the particles are moving in any way you like relative to the position that they define by their triangle, so to speak. But in a Machian way, because of that best matching requirement, they are very strongly restricted. And what that means actually is that it corresponds to zero angular momentum. So the total universe in a Machian system can only have vanishing angular momentum. And that's a very powerful restriction. And I'm just going to go through the equations here for the 6 or 7 people who are familiar with theoretical physics. This will mean something to you. For the rest of you, it won't mean much. But I want to get down to the formula at the end of the thing there. So this is a variational principle, which is, This is a variational principle which has no time in it because, while I operate, I think it'll be all right, thank you. It doesn't have any time in it. This lambda here is just labeling which triangle is following after another. I'm going to still talk about triangles. And I'm going to minimize a certain quantity. This capital E, I've done it again, this capital E is a constant which will turn out in Newtonian terms to be the total energy. This is the potential energy, the Newtonian potential energy. And this quantity is very like Newtonian kinetic energy, but it's derived from that quantity that I was minimizing in the best matching process there. And then you have the standard rules of variational calculus. You get what are called the Euler-Lagrange equations. And they come out looking like this. And they're rather ugly because of this quantity here, which is on both sides upside down compared with there. Now, the first thing you want to do when you get an equation like that is simplify it. So, and your lambda is completely at your freedom. It's a completely arbitrary parameter. It's not an absolute time. So you can choose it how you like, and you can always choose it so that this t quantity here, which will depend upon your choice of lambda, is always equal to this constant minus the value of the potential in the configuration at which you are. And then that rather ugly equation reduces to Newton's second law. And you've recovered Newton's dynamics exactly in that particular frame of reference achieved by best matching, and with that strong restriction that the angular momentum must be exactly zero. But then, if you write out what this choice means, that I've chosen lambda such that that is there, you actually get an explicit expression for the increment of time, how much time in Newtonian terms has passed. And now you get an explicit expression, and it's come about because of all of the changes, the differences in the best matched position. So I've got the whole universe, 1 billion particles. I move it into the best matched position. I get these best matched quantities here, which went into my variational principle up there. BM stands for best matched. So I get that there. So I've got an explicit expression. So time in this, and it's divided by here. I won't go into why this is actually the only sensible choice you can make for time, but take it on trust, if you will, that it is. So the increment of time is the distillation of everything that has changed in the universe. It's a distillation of difference. And let me just remind you one of the most famous sayings of Ernst Mach. It is utterly impossible to measure the changes of things by time. Quite the contrary, time is an abstraction at which we arrive from the changes of things. And that is completely explicitly given to you there. And in Einstein's general theory of relativity, you have something which is very similar, but much, much more sophisticated, wonderfully sophisticated. And let me just emphasize, which is, I think, bringing this into some of the concerns of this meeting, is that this is doubly holistic, this expression here. First of all, it's holistic because I'm using those best matched quantities. So that's holistic. I have to compare two complete configurations of the universe to get those quantities that go into it. And then I have to add them all up to get my little increment of time. So it is very holistic. And I think actually I'm getting more and more convinced that reductionism is completely and utterly false for describing the universe. And it was introduced by Newton somewhat inadvertently when he introduced absolute space. Because nothing can be simpler than the idea that there's an absolute space and a particle moves uniformly in a straight line. And I would say reductionism in modern science goes back to that decision of Newton when he created dynamics. But it was fundamentally and utterly wrong. And I think actually when you analyze the structure of general relativity, there is a way of analyzing it which makes that quite clear, that it was a wrong way to do it. So let me just show you how space-time then emerges. So you get Newtonian space-time by this way. I got my triangles into the best match position. I start with my first triangle, and I keep on moving all the successive triangles into the best matched position, one above each other, and I separate them vertically by that increment of time that I just got, and that creates in this way exactly the Newtonian framework of space and time. It's all there, but it's all done in Machian terms. And in a much more sophisticated way, Einstein's theory arises in the same way. Now I want to go on, jump straight on to an attempt to create quantum gravity, which dates back to 1967, the famous Wheeler-DeWitt equation. Now let me just remind you that quantum mechanics, in the form that it was discovered by Schrödinger, is defined on configuration space. It gives you, and this is responsible for all of the really incredibly wonderful things in quantum mechanics, the wave function in quantum mechanics as created by Schrödinger is defined on configuration space. If I have three particles, now he formulated it in Newton's absolute space and time, but if I have a system consisting of three particles, there are probabilities not for individual particles, but probabilities for all possible triangles in all possible positions, say in this room. Suppose we're talking about 3 particles in this room. It's mind-bogglingly large what the arena that quantum mechanics explores. So it's every possible configuration of the system in every possible position in the room is given a certain probability by Schrödinger's equations. And so this is expressed here. There's a probability for the configuration which is expressed in terms of this square of the wave function. And Schrödinger introduced this wave equation here in 1926. I've forgotten the mysterious I, the enigmatic I. Apologies for that mistake. There should be the imaginary root of 1, minus 1 there. But now in 1967, when DeWitt tried to do this for the whole universe, to try and find a wave function for the universe, what he found decidedly disconcerting was that the bit to do with time just disappears altogether. This bit there just wasn't there at all. There was just this thing equal to 0, h sine. This is the notorious Wheeler-DeWitt equation. Now, in full quantum gravity, nobody's ever succeeded in making mathematical sense of that. You can make perfectly good mathematical sense of it for particles in say, Euclidean space as an analog of it. And it is, in fact, actually just what is called the time-independent Schrödinger equation, which is interesting. The first equation that Schrödinger found, and I believe is actually the most amazing discovery in science, because it's the equation which explains why things have shapes. It's the equation which explains why molecules, you put the ingredients of a molecule together, and then it will tell you what are the shapes it can have in a stationary state. It explains why the water molecule is the shape of a banana and things like that. And I think this is actually, he solved the problem that had been perplexing thinkers since antiquity. Where do all the wonderful shapes in the world come from? And I think this is ultimately what you should think of at the time-independent Schrödinger equation. And for me, it's actually much more fundamental than the time-dependent one, if this is right. Now, what's the simple reason why DeWitt found that equation? Well, it's ultimately to do with the fact that sitting inside general relativity, there is that theory of duration that I told you about. And it's a manifestation of that leads to it. And the result is very bizarre. It says the Wheeler-DeWitt equation of the universe, it gives static probabilities for configurations of the universe. So each possible configuration the universe could have is associated with a probability, and that's it, period. Nothing more to be said. So how can we make any sense of that? And that's called the problem of time in quantum gravity, and it's been exercising people for 50 years now. Now, I think that the way we can begin to understand this and interpret it is through what I call the notion of a time capsule. And I'm showing you here, no, I'll define first of all, a time capsule is, and I don't mean something that people put in the foundations of a house with a record of what was going on at the time the house was built. I would say it's any static configuration, that appears to contain mutually consistent records of processes that took place in the past in accordance with certain laws. I don't know how many of you recognize this picture, but it's a very famous picture which nearly got Ernst Mach the Nobel Prize. It's the flash photograph he took showing shock waves. This is a bullet going through, piercing a membrane, and it triggers a flash. And that is a time capsule if you know how to interpret it properly. This is, so to speak, the consequence. Back here is what was happening is a consequence of what the bullet did earlier. The whole history of the bullet as it moved from there to there is recorded here in that picture like that. So in one static thing, there is a whole history represented there. Now there's much more wonderful examples than that, I think. Let us think about deep time. We had mention of when the Earth was created. 6,000 years ago yesterday. Now, what led to the overthrow of that biblical story? It was actually static configurations of rocks and fossils. The evidence from geology, which was unearthed about 200 years ago in Napoleonic times, they found people started looking carefully at rocks, the strata of rocks, the fossils they could find in them, and they found correlations between it. Science starts when you find correlations. And when they looked at it long enough and they thought hard enough about it, they said, this tells a story of deep time, of an immensely long history. The Earth must have an immensely long history. It must have come through a process to leave these records behind. But it's all static. And you can go out and see the very same rocks and fossils where they were when these people 200 years ago discovered them. Essentially, they've not changed. It's all there. It's all in one configuration. Now, there are, everywhere we look in science, and in fact, why does it all cohere to make a great story? Is everywhere we look, we find time capsules, correlations in very, very different structures. But when we look at them and learn to interpret them, we find they all tell the same story. There's the memories we can access in our brains. There's the astronomical heavens at all wavelengths, tells this fantastic story. There's the DNA in all our organisms, and everything tells the same magnificent story, starting with a very special Big Bang. This is David's past hypothesis. Let me just quote from Shakespeare now. I can't resist it. At the end of the Midsummer Night's Dream, Hippolyta says to Theseus, "'Tis strange, my Theseus, that these lovers speak of." Theseus is very deflationary. More strange than true. The lunatic, the lover, and the poet are of imagination all compact. And as imagination bodies forth the forms of things unknown, the poet's pen turns them to shapes and gives to airy nothing a local habitation and a name. To which Hippolyta responds, "But all the story of the night told over, and all their minds transfigured so together, more witnessless than fancy's images, and grows to something of great constancy." One of the greatest lines, I think, in Shakespeare. Intersubjectives, or objectivity. It's a fantastic story, and it's all in static form. You can read the Midsummer Night's Dream. It's all on the printed page. It's all there if you want it. Now, I'd better get on briefly, quickly. I want to say, why do we see motion? Now, Galileo was the person who, in the modern age, first of all, clearly made the distinction between primary and secondary qualities. To excite in us tastes, odours, and sounds, I believe that nothing is required in external bodies except shapes, numbers, and slow or rapid movements. I think that if ears, tongues, and noses were removed, shapes and numbers and motions would remain, but not odours or tastes or sounds. The latter, I believe, are nothing more than names when separated from living beings, just as tickling and titillation are nothing but names in the absence of such things as noses and armpits. Lovely little bit of sensuality there. One of the greatest writers of Italian prose, Galileo was. By the way, there was mention of Thomas Hobbes. Thomas Hobbes visited Galileo when he was in house arrest, and got the idea that motion could explain everything, including what was going on in our brain. So it was a huge event in Hobbes's life, and led on to the Leviathan and everything really that Hobbes wrote. But the question I ask is, Galileo perhaps made the right basic division between primary and secondary qualities, but should perhaps motion be shifted from the primary qualities to the secondary? And is it perhaps our consciousness that is giving the impression that my hand is moving. Nobody believes that, well, very few people believe that green is out there, it's wavelengths of light out there. What about motion? Is it really there? Now, at the FQX, the Foundational Questions conference I was at, and so was David and Bernard and George, there was a very entertaining neuroscientist, David Eagleman, who does lots of these experiments which show how the brain presents us with a narrative. It interprets things for us and very often tells blatant lies. It reverses the order in which things happened and presents them to us in the wrong chronological order, if it thinks that's going to help us and help us make sense of the world. So if it can do that, it's halfway on, I think, to saying that somehow the brain and the consciousness is creating the impression of motion. And if you think about it, what evidence do we have for the past? I would say there's only 2 bits of evidence we have for the past. It's the mutual consistency of records, and it's the actual seeing of motion, that 1/10 of a second where I actually, like you, see my hand both there and here and moving. It's all there. And I don't think there's any more evidence for the past than that, with the evidence from time capsules. So where could all this come from? And I am drawing to a close now because I've gone over time. Here we are again. There are 2 great asymmetries, I would say, that I can identify. The one is, of course, between birth and death, the past and the future. This is of intense personal significance to all of us. But I want to draw attention to another huge asymmetry, which I don't think has had nearly the attention it deserves, which is what I say between uniformity and complexity. If I have, and of course it's very difficult to define complexity, but if I have that, I've shown it to you yet again, that doesn't seem to suggest very much. But if I have 100 dots, I can produce a quite amusing little cartoon with 100 dots. And suddenly there's some meaning in it. And there's something very fundamentally different between just random collection of dots and ones that are ordered in some way and tells some sort of story. Now, the space of all configurations is highly asymmetric. Here's a picture of the way I like to think about the world. I call it Platonia because each configuration for me is a Platonic form. It's a mathematical form. Now, the thing that's most remarkable about configurations and a configuration space, so what I've called, a plague on this pointer. What I've called Platonia here is the configuration space of the universe. Each point inside here is a possible configuration of the universe, and this is us here in Yale. Now, when you think about these things, it's a very, very striking fact that there's always one uniquely distinguished point, one uniquely distinguished configuration, which is a point in the configuration space, which is unambiguously there, and I call the point alpha. Now, if you don't allow scale, if you say only shapes count, and just consider triangles, consider all possible triangles, there is one triangle which stands out and is uniquely distinguished compared with all the others. It's the equilateral triangle. And notice we speak of the equilateral triangle, not an equilateral triangle. That is point alpha. I think it is extraordinarily suggestive that we seem to live in a universe which appears to have emerged from a Big Bang which was remarkably uniform. This is essentially the past hypothesis. At least the geometry was extremely uniform. I think that is very, very suggestive. I think this could completely change the way we think about the arrow of time and where it comes from. Particularly if you take the Wheeler-DeWitt equation seriously and say that the Wheeler-DeWitt equation is about is a law which distributes a static probability for each configuration there. Each configuration, every single one, has its own probability. Now, it's like the time-independent Schrödinger equation. the time-independent Schrödinger equation contains nothing whatever to do with time. It just has, it's an equation, and it has to satisfy certain conditions. Being square integrable, the solution has to be square integrable. That's nothing to do with time. So maybe the explanation of all these things is something to do with how that probability, if we take the Wheeler-DeWitt equation seriously, and by the way, it's very hard to avoid taking the Wheeler-DeWitt equation seriously. You may dismiss it because the mathematics is so damnably difficult, but the route to get to it is almost inescapable. You're driven to it just by the way quantum mechanics and general relativity work. What determines where the probability is distributed on Platonia, on the different possible configurations? Now, I conjecture, and it's a conjecture and I've no good mathematical evidence to support it at this stage, that it's the shape of Platonia that gives high configurations to some, high probability to some configurations and low probabilities to others. And the ones to which it gives high probabilities are time capsules in the sense that I defined it. And that comes about because of the asymmetry of the configuration space. And in its most extreme form, that's why we're here now, because the Wheeler-DeWitt equation gives a high probability to this configuration. Now, this is a pretty wild dream. So that's my explanation, possibly, for the arrow of time. It's nothing to do with a past hypothesis. It's to do with the asymmetry of the configuration space. So, I mean, this is the mystery of that people like Roger Penrose have been concerned with for half a century. Why did the universe begin in a Big Bang with a remarkably low entropy? Well, I think the mystery may exist because we postulate eternal laws and contingent initial conditions. This came out very clearly in George's talk yesterday. But if time does not exist, there cannot be initial conditions, but only eternal laws. And as Kepler said in a different context, we must philosophize about these things differently. Let me get Kepler up there. Whoops, I've gone too far. We must philosophize about these things differently. So I have this. George had his vision yesterday, and a very noble one it was too. I have a vision too. And in fact, I'm just going to go really wild and say that I think possibly science up to now is only beginning to scratch the surface of things, and that there's an infinitely rich physics still to be discovered. A meeting like this allows these fairly wild speculations. I would conjecture, I said yesterday, I cannot see how Darwinian evolution can explain, it can explain the behavior of love, the mother looking after the child, or the siblings helping another sibling. I don't think that it can explain the sensation of love, or the sensation of taste. Any of the qualities, any of the things that make life worth living are completely inexplicable in standard science. Now, I really wild conjecture, perhaps it is that we should think of the qualia as being active in the same sense as dynamical degrees of freedom are in physics. And perhaps there is a vastly richer physics out there which we haven't begun to get to. And that this will be a more unified thing. It will be very much top-down. And I'm going to finish with, first of all, a little bit more from Shakespeare, and then one last bit from Leibniz. Bottom wakes up and says, "I've had a most rare vision. Man is but an ass if you go about to expound this dream. It shall be called Bottom's dream, because it hath no bottom. It's infinitely deep." Let me just go back to where was it? There is inescapably an alpha, a configuration that is the least interesting in any configuration space. But there is no omega. So far as I can see, as you go out here, you get to potentially to ever richer and ever richer possibilities. That's Bottom's dream. It hath no bottom. Now, I said that I think that if you get rid of time, there is a way of beginning to, that science might address the question of why and not just how. And my last slide will show you something which I think illustrates that. It'll mean very little to you unless you happen to have read an article by me on the principles of Leibnizian philosophy. But the idea behind this came from Lee Smolin, who tried to give mathematical expression to Leibniz's idea that we live in the most varied of all possible worlds. And I'm grateful to Julia, who's here, for pointing out to me that Leibniz, when he made precise what he meant by that we live in the best of all possible worlds, for which, of course, he was mercilessly attacked by Voltaire in Candide, to make precise what he meant by the best of all possible worlds, it is that we live in the universe, the world that is more varied, but created by the simplest possible laws. And in fact, this is an example of it. What created this pattern? There's 24 slots there, and you can put in it balls of one of two colors. And you must do it in such a way that each ball can be more readily and more easily identified than any other. So that each place where you look is more different, is very distinct from any other. So if I want to identify one particular thing, I can say, the ball that I'm looking at has got two balls of the opposite color to either side of it. I can't say which side of it is, and I can't say whether I'm looking at a blue or a red one. In fact, you may have spotted I was looking at that one there, which I think is uniquely distinguished. Now, this is a pattern here. This is an illustration. This is a Leibnizian world. By the way, there's no sense of time coming into this. But it is a Leibnizian world which is more varied than any other. It is the ontologically richest world that can be created, configuration that can be created, subject to the rules, which there were 24 slots, which was the maximum my Macintosh could do 20 years ago. And according to those rules that I did. And above all, it's all about identity. Leibniz is always about identity and distinguishing things, and that there must be no two things alike. So this is, in a way, it is the ontologically richest configuration that the universe could have. In this case, it's unique. And this, quite interestingly, by the way, this is about creating variety. But what I found, when you go through, you always find that when you try to create variety, you inevitably create quite a bit of uniformity to go with it. And I just begin to wonder whether this isn't what Leibniz was on about in his Theodicy, that you cannot create a good world without some evil in it. So you see down here, except for this one thing here, this is a pretty dull uniform stretch. The interest is up here where things are changing a bit. So I leave you with that thought. I think that taking time out of our conceptual framework could enable us to begin to ask the question, why, and not just how. Thank you very much.
Thank you so much. We'll have a 5-minute break followed by Jill and Laurie. And we really mean 5 minutes, okay? No, you were not on. You were exactly on time in many ways.